Yeah, it's like 4:32 in my clock.
Nice. Okay.
Okay, I think let's start today's seminar. So let me welcome today's speaker, Dr. Uditendu Mukhopadhyay, who did his PhD from TU Delft QTech Institute from 2015 to 2019. Uditendu worked in various things, including what he's going to talk about today about ferromagnetism in a gallium arsenide and aluminum gallium arsenide quantum dots. Apart from that, also there are other works of Uditendu. So thank you, Uditendu, for agreeing to give a talk in our seminar series. I welcome you, and I also welcome all the participants. So today we have a different way of asking questions. So usually we ask random times, but today we will take only 2 breaks. So after the introduction part of the talk, then we will take a break and we can ask question at that time. Also, we will take questions from YouTube as well as from the Zoom chat box. If you want to ask a question there already, you can do that. Good. Thank you very much, Uditendu. Please go ahead with your talk.
Hi. Hello. Good afternoon, everyone. Let me start by thanking you for organizing this talk and thanking all of you for attending it. So today I'm going to talk about our experiment in quantum simulation of Nagaoka ferromagnetism in a 2x2 quantum dot array. This was the main part of my PhD. As I can see from this title, there are many kind of words here that might not be readily kind of available to all of you in the audience. So I'll take some time to introduce each of these in some detail, and then we'll take a few questions, and then I'll go into my main experiment. So to start with, let's talk about the main thing, Nagaoka ferromagnetism, what it is. So I'll take a step back and look into the history of ferromagnetism. So there is this Stoner model of ferromagnetism that was one of the first. And the idea here, the Stoner model comes from a mean field decomposition of Hubbard model. In Hubbard model, any electron or all electrons are free to move around in the lattice, in the Hubbard lattice. So this is basically a form of itinerant ferromagnetism where electrons move around. And that's why Stoner got his criteria of like the band splitting, which increases kinetic energy, magnetization decreasing U, and you have this competition, and that gives us the Stoner criteria. But later, so the idea is Stoner model in principle should be an itinerant ferromagnetism. But later it was found out that the well-known metals, iron, nickel, cobalt, they are not completely itinerant ferromagnetism. Yes, electrons move around, but this is still, people call it like somewhat localized magnetism. And then there was a continuous debate of whether this complete itinerant ferromagnetism can even exist in practice. And in this context, Nagaoka ferromagnetism is a very good example, or is a big point. So in this paper in 1966, what Nagaoka showed is if he takes a 2D lattice, where the lattice follows Fermi-Hubbard model, he fills the lattice with one less than half filling. So half filling is 1 electron per side. So he fills this infinite lattice with 1 electron per side, and then he takes away 1 single electron from this entire ensemble. And you have infinite U, you have equal T, so electrons can move around throughout the lattice. And in this limit, what he showed that the ground state of this system is ferromagnetic. Now, since then, like since 1966, there have been several theoretical studies around Nagaoka ferromagnetism, but so far, or before our experiment, there hasn't been a single experimental demonstration of it. So the thing Nagaoka based his calculations in this paper is Fermi-Hubbard model. This is probably clear to all of you, but I'll just take a small moment to explain. So in Fermi-Hubbard model, we have 2 main energy scales. There is this on-site interaction U and tunnel coupling T, which in the basic form of Fermi-Hubbard model, it is actually confined to nearest neighbor interaction. So electrons can only hop from one side to this nearest neighbor. Although this looks quite simple, the solution of Fermi-Hubbard model is not simple. In 1D, we have Bethe answer that gives us the solution. In 2D onwards, the solution, there is no like analytical solution for the general case. Okay, for Nagaoka's case and for some like specialized versions, you might have some analytical solution. Even if you go for like a computer simulation, the quantum correlation present in this problem actually blows up quite quickly and exponentially. So up to like a few tenths, I think, is the limit of what you can completely simulate in a computer, in a classical computer. Although, if you look at what is actually predicted from a Fermi-Hubbard model, there are like host of really nice phenomena, like high TC superconductors are supposed to be coming out of this Fermi-Hubbard model, also pseudogap physics, and several others. So what happens is now, so how do we actually simulate a Fermi-Hubbard model? And that's where the idea of Feynman comes in. So in 1982, Feynman gave a lecture where he proposed that we can't simulate a quantum mechanical problem in a classical computer because of this exponential scaling of requirement of scaling in resources. So what he proposed instead, that will simulate one quantum system with another. So this is the idea of quantum simulation. So since in 1982, quantum systems were still very difficult to actually prepare, even control, measure. But since then, mainly in the last 2 decades, there have been several experiments. And now, when people think about quantum simulation, there are 2 main ways we think about quantum simulation. It is actually very close to a classical simulation. Let's say we want to simulate something classical. We have a air tunnel, and we want to simulate the air drag on a car in this air tunnel. We can do it in 2 different ways. We can either make a computer model of this entire problem of the car and the air, and we can do this entire simulation in a computer, or we can make a toy small scale model of both the air tunnel and the car and actually measure how the air drag is happening. Quantum simulation is actually very similar. So the analogous to the first one would be something that is now known as digital quantum simulation. So in digital quantum simulation, if you have a quantum processor that is highly programmable, you can take your problem of interest and you can actually transform this problem into quantum gates and use the quantum processor to run this problem Hamiltonian and get your answers. This is the digital way of quantum simulation. And if you think about it, this is very close to the traditional way of what we think of quantum computation. There are 2 differences. One is in quantum simulation, people still don't think about error correction, which is an integral part of quantum computation. The other thing is in quantum computers, people generally have a claim of universality, whereas a digital quantum simulator can be like a processor that can simulate one or a few problems. The other way of doing quantum simulation, which is more relevant now in this noisy, like small scale quantum devices era, is the analog quantum simulator. So it's the same thing. So we actually make a toy scale model. So we take a quantum system that is very close to the system of our interest, but more controllable. Next, we map the system of interest on our toy quantum system that we can actually control, and then we get answers from this toy model. And this analog quantum simulation has actually made a lot of stride in the last 2 decades. One thing to note in analog quantum simulation is you can't take any toy system and simulate any other problem. The similarity has to be sufficient to start with to do this. So to take some examples, like an ultra cold atoms are good in simulating Fermi-Hubbard model. Up to some point, there is some limitation on like what kind of T's and U's you can go to. So there have been several really nice papers out of the ultra cold atom community, whereas both trapped ions and Rydberg atoms have been highly successful in simulating Ising models. But it would be very hard to simulate Fermi-Hubbard model in a trapped ion system because there is the inherent like similarities has not been that well established at the moment. So in this context, I would now like to introduce our system. Our system is a gate-defined quantum dot. And these gate-defined quantum dots are also very good simulator of Fermi-Hubbard model. So let me first introduce what these gate-defined quantum dots are. So gate-defined quantum dots, or I'll call them quantum dots from now on, are basically islands of electrons. You can think them as a 0D island. So you confine these electrons in all 3 directions, and that's what gives you quantization of energy levels. And then you fill electrons in there, you can control several things. So the first thing we start with is a 2D electron gas. So for my system, what I have is a aluminum gallium arsenide heterostructure. When we put some delta doping of silicon dopants, electrons, because of the band bending, electrons comes to this interface. So about like 80 to 90 nanometer below the top of the heterostructure, the surface of the heterostructure, we have a 2D electron gas. Electrons can move freely in this 2D plane, but cannot move out of this plane easily. So we now have one degree of confinement. So the next confinement, so I need to confine electrons from 3 directions. The next confinements come from gates that we actually put on top of this heterostructure. So what we do is we use the lithographic techniques to put metal gates on top of the heterostructure. So in this picture here, these yellow lines are actually gates. Now, what we have underneath is electrons. So if you put voltage on these gates, the voltage, depending on what kind of voltage you put, you can attract or repel electrons. So in this picture here, what you see in blue is basically where we have electrons. These pillars are basically ohmic contacts from the top of the heterostructure to these electrons. These are my reservoirs. And by depleting electrons in this pink or orange region here, not pink, orange region here, we create these islands of electron where I can now control how many electrons are in. This is a top view of the same system. So these are my gates here. And I have these dotted circles are where the electrons would be 90 nanometer below this surface. There is another electron, the reason for which, another quantum dot, the reason for which will be clear in a minute. So,
sorry to interrupt,
sure.
Shuddho here.
Yeah.
Sorry, Shomo, it seems there might be a login issue with some people, is some messages I'm getting.
Oh, but what kind of login issue means? You have to just, I said, no, that you have to log in means.
Well, if you
I
check
think
in
this was in the email from
many people are waiting outside.
They're on YouTube basically, but it's up to you. If the security
now I cannot change the authentication, so this is an authenticated method. Just you have to log into your own account and then it should be okay.
So I actually face this issue. So it's just that you have some Zoom credentials, like with which you made your Zoom account. You just have to input those. And that
exactly.
Yeah.
But
so right now I cannot change it. So
YouTube is on. No?
Sorry.
YouTube is on. No?
YouTube is on. YouTube is on.
I can ask questions on YouTube.
Yeah.
Maybe you'll have to look out for YouTube chat.
Okay, let's continue maybe.
Okay, thanks. So, so that's how we make the device. The next thing we do is we put it in a dilation refrigerator, and that takes the electrons, electron temperatures to around say 80 to 90 millikelvin. The sample goes to 10 millikelvin, and a combination of all these gives us. And the reason we need to put it in a dilation refrigerator is because this quantization of levels, the energy gaps in room temperature is not high enough to actually have like put electrons in one orbital and not have it hop between other orbitals. So this is how a quantum dot system is basically made. So should we take a break now or maybe a bit later?
It's up to you. We can take. There are one or two questions.
Okay, we can do three breaks. So now first,
sure.
The first one now. Yeah.
Sure. So let me just then read out the first question. So there is one question in the chat. It says that not clear. What kind of ferromagnetism is this?
This is a ferromagnetic. So basically what Nagaoka did is he started with the assumption that you have a 2D lattice. You put half filling. So you put one electron per side in an infinite lattice where your U is also infinite. And then you take out one electron from this infinite lattice. So you have like n-1 electrons in the lattice. You let the electrons move freely throughout the lattice and the ground state of this system becomes ferromagnetic. So that is the origin of this ferromagnetism.
Okay. So
it's an itinerant ferromagnetism because all electrons are moving freely throughout the lattice. And yeah, I'm not sure if I answered the question.
We don't have any other question in the YouTube, but I have a small question. So you mentioned that in the ion trap, you cannot realize Fermi-Hubbard model. Can you please explain once more what is the difficulty there?
No, so basically what you need, as I'll show for our case, like you need a direct correlation between what would be your Hubbard U, what would be your Hubbard T. And I don't think in ion traps they have still like the analogous versions of U and T in their control parameter, or at least one of them in their control parameter. What they can control is the Ising parameter because the interaction is more Ising-like.
Right. But in also in cold atom, right? So in the cold atom, they have realized it.
In cold atoms, they have realized it because of something called fetchback resonances.
Right.
That so they introduced this, which then allowed them to model Fermi-Hubbard model in cold atom. So I'm not saying it's impossible. I'm just saying I don't think they have realized it yet.
No, as you said, in the cold atom, they have definitely realized it, but
yes.
maybe ion trap not yet.
For ion trap, I don't think they have realized it yet. Cold atoms, they got phase-back resonances that later allowed them to do Fermi-Hubbard simulation in cold atom.
Yeah. Right. There is one more question by Parth. Parth is asking, what kind of benefit exactly does quantum dot-based system have over trapped ion or Rydberg atom? I think that kind of answers already.
Yes, but I
want
would
to elaborate.
Answer,
you can.
I would answer. So with respect to Rydberg atom and trapped ions, yes, I already answered, I think. So the interactions are different. With respect to cold atoms, I will try to answer them in a few slides, one or two slides.
I just had a quick comment. You know, Ketterle's group, I'm Urjit Yagnik. The Ketterle group actually in 2007 or 9 simulated Stoner ferromagnetism in the cold atom system by reversing the sign of this BEC.
Yes.
Okay, so we don't have any more question yet, so we can continue. And then we can take 2 more breaks actually. Yeah.
Sure, I will take 2 more breaks. Okay, so next is, so now I have already explained how we actually make the quantum dot system. I will talk about a few basic controls of these quantum dots that helps us in doing the experiments, and then I will move into the actual experiment. So the first thing is, I was continuously talking about how we can confine a certain number of electrons in a quantum dot. Let's see how we can do this. So the thing we do is, so we have, say, let's talk about now this one single quantum dot. So I have 2 reservoirs here. I have 1 quantum dot, and I put a bias in one of them, and I measure the current through this quantum dot. Now I have a quantization of energy level, and this energy quantization, like the energy levels can be modified. So like these levels can be put up and down by changing the voltage here. What we do first is we put a bias, so the source and the drain has some difference. And if we measure the current that is going through the quantum dot, in a condition like this, which we call the Coulomb blockade region, where there is no energy level of the quantum dot between this bias window, we will not see any current. Now, as we change the voltage of the plunger gate, that's this gate, this energy levels will either go up or down depending on what you are doing, positive or negative voltage applying. And then when you are actually within the window, you will see a certain spike in current. And that is when 1 electron is continuously passing through this quantum dot. So now by counting this number of Coulomb peaks, so these are Coulomb blockade peaks. Now counting the number of Coulomb blockade peaks, so what we do essentially is we keep on applying negative and negative voltage until we don't see any Coulomb blockade peaks anymore for a significant region. So like say here, my gap between two peaks is like 20 millivolts. So I would be confident that there is no electron if I don't see a single peak within say 200 millivolts at some point. So that point I say that there is no electron in the quantum dot, and then I cross a certain number of peaks, and let's say if there is no electron here, then here I will have 1 electron in the dot, here I'll have 2 electrons, and so on. So by doing this, I can actually have a certain number of electrons confined to a quantum dot. This is a very nice technique, but the problem here is you will always have to kind of run to measure like how many electrons you have to run current through this dot, which might not be always nice. So there is a technique which came on a bit later that helps us. It is kind of a sensor kind of technique. Okay, one more thing is using this gas, we can also measure what is the energy difference. So all we need is some kind of a lever arm that we know from a bias triangle. So we know like this millivolt, how to convert it to milli electron volt or micro electron volt. Like we know the lever arm. Okay, so the next thing we do is we don't want to pass this current through the quantum dot, the dot that we are actually interested in. So that's why we have this capacitive coupling between, so this is my main dot array and this is my sensor dot. My sensor dot would still have current running through it. My main dot array will not. And these two are capacitively coupled. And what I do here is I align or I put the voltage of one of this plunger, the sensor dot plunger, in a flank of a Coulomb peak. So this is a very sensitive region. If the environment, the charge environment around this this dot changes slightly, you will actually see a jump in current. So we continuously measure the current level here. Now, if any electron goes in or out of this quantum dot or any of these three quantum dots, any adjacent quantum dots, you would see a jump in current level. And what we do is then take a derivative. So this is this kind of figure I'll keep on showing you. This is called a charge stability diagram. So instead, like where these are, you can see three kinds of lines. There is one line that has this angle that is more vertical. There is one line that's this angle that is more horizontal. And there is this avoided crossing between, I'll call them vertical and horizontal lines. And there is this line, which is the interdot line. So again, this is the derivative of the jump in the Coulomb, the charge sensor signal. And that the derivative comes up as a line. Otherwise, you would just see a shift in current. Now, again, you can calculate the number of lines you are crossing. So again, what I'll do is the same thing. I'll go for a region where I don't see any more lines. I know this is my 0, 0 region. So this is the electron occupancy of these two dots. P1 is this gate, which is more coupled to this line. So that means this is coupled to this dot, whereas P2 is more coupled to the right dot. So if I cross a vertical-ish line towards the left, I am removing one electron from the left dot. If I cross a horizontal-ish line towards downwards, I am removing one electron from the right dot. And by now counting the number of electrons, I can go to like these gate voltages, say -50 and 0, roughly here. And I know that my system of these two dots will have 2 electrons in each side. So this is the first basic control. So by using charge sensing, we can know how many electrons we have in the sample any time. The next thing we want to do is we need to have some kind of a control over tunnel coupling. And the reason we do is we zoom in into one of these regions where we have an avoided crossing. We measure the charge signal here. So now here it's not a derivative signal, it's just the original signal for kind of understanding this better. I measure the charge signal signal here, the charge sensor signal here, and I can fit this with a tan hyperbolic curve, which gives me the tunnel coupling between the two dots, when one electron is shared between these two dots. And this is my kind of measure of tunnel coupling in a system, and I can change this tunnel coupling by changing different gate voltage. Now that I'm equipped with these two, let me show you how a quantum dot system is good in simulating Fermi-Hubbard model. I'll again look into the basic Fermi-Hubbard model. I have the U's and T's. Before I was keeping the U outside because I was assuming all U's are same and all T's are also same. In a practical system, you don't have that liberty, so everything goes inside the summation. So I had different U. U is the on-site energy. So in quantum dot language, what U is the charging energy. So it is the energy needed to add one more electron to a dot while another electron is actually present, or due to the presence of other electrons in the dot. The tunnel coupling is basically the T is basically the tunnel coupling between the nearest neighbors. On top of these, we have two more energy scales. So the first one is this mu, which is the local energy. I already explained to you before, I can change the energy level of each dot. And that is the local energy. I can change this by changing different gate voltage. Finally, I also have an intersite interactions because I have electrons. It doesn't matter if I add an electron here, it will still feel Coulomb repulsion from the other dots. So this is the energy penalty that you pay to add one electron due to the presence of electrons in other sides. So the typical energy scales that we can achieve are these. And out of these four, our T and mu are gate controllable. So generally, we control the tunnel barrier, the tunnel coupling using these tunnel barrier gates, which is the gate that is between two dots, whereas we control the mu by changing these gates. But there are also cross capacitances that one needs to take care of and all kind of like experimental things. The other two energy parameters, U and V, we can measure them from charge stability diagram quite accurately, but we can't actually control them very well once a device is made. On top of this, our KBT, like the thermal energy, is way lower. So you can see that this is orders of magnitude lower than even the tunnel coupling. So we can reach this highly sought after limit of Fermi-Hubbard model. And that's where I think we are slightly better off than the cold atom community. So these energy scales, they are still not like, they can either reach the T tunnel coupling very higher than the KBT regime, whereas the U would be closer to T, where otherwise they can reach the U greater than T regime, but then that tunnel coupling would be very close to the thermal energy. So I don't think they can simultaneously reach this limit as of what I know, like what I've seen so far in their papers. But these fields are changing very quickly, so you never know when they will start doing that. So now that we have all this control, in 2017 in our group, we have shown that using this device, we could actually do a quantum simulation of Coulomb blockade to collective Coulomb blockade, which is a small scale analog of metal to Mott insulator transition. So in the regime where your T is lower, we saw Coulomb blockade regimes, whereas when we went to the collective Coulomb blockade regimes, which is analogous to like the metal regime, the T was higher. So this is, I think I'll take a break now for if there is any question, I'll then.
Sure. So there are two questions. For instance, one question is what's the difference between UI and Vij term in the previous expression?
Okay, I think I explained this, but let me just, if I was not clear, let me restate. So U is the on-site interaction. So you have this quantum dot, let's say I have this quantum dot 1. U would be the energy penalty to add one electron to this quantum dot because of presence of electron in that same quantum dot. Whereas Vij would be the energy penalty to add one electron to this quantum dot because of presence of electrons in the other quantum. So that is the difference between U's and T. So this is on-site interaction and inter-site interaction.
So maybe there is an I not equal to J in that last one.
Oh yeah, sorry. Yes, that should be there. You said two questions.
So can I ask one
Sorry,
question?
Yeah.
I'm Subhabrata.
Yeah, please.
Hi.
Hi.
So my question is related to other source of interaction. Like this is embedded in a system. There are some environment. There could be nuclear spin and all these things that can also affect.
Yes. Yes. So nuclear spin in a gallium arsenide system is of the order of, like the energy scales is of the order of nano electron volts. Similar is spin orbit interactions. It actually plays a role not directly in Fermi-Hubbard model, but I will show you in our Nagaoka experiment, both nuclear spin and spin orbit interaction plays role.
Okay. Okay.
But the energy scales are quite low in terms of Fermi-Hubbard.
I see. In this particular system.
In this particular system, yes.
Okay. Thank you. Thank you.
So we have two more questions, Vizendu. One is also my question actually. So usually in the cold atom, you can get up to 100 atoms, right? And
yes.
do that. So here it seems only 3. So what is the scalability of these kind of devices?
So in my experiment, it was 4. I have a plan to go to 8. That doesn't seem, or 8 or 10. That doesn't seem too difficult to me, at least in PowerPoint. But yeah, cold atom has a much higher scalability there. Also, their measurement is slightly better because they can do a single shot snapshot measurement, what we can't do. But they can't do correlation measurement that we can do. So there are like advantages and disadvantages of cold atoms and quantum dots. And like an ideal system would be a cold atom quantum dot mashup or something like that.
Okay. So there is another question by Sai. He is asking that why does the current jump in the chart CB peaks diagram vary with plunger gate voltage?
No, it doesn't vary with plunger gate voltage. So if you go to this regime where you don't have any electron in this quantum dots and you are not adding anything, so like here and in more negative regime, you change the plunger gate voltage, there would not be a jump. There might be a drift because of capacitance coupling. The jumps come in when you have an electron either going in or out of a quantum dot.
No,
so this
yeah, that I understand. In the middle diagram C, with the red CB peaks indicated, the middle lower diagram. Yes. So the height of the peak seems to vary somewhat randomly as you go from left to right.
I think this is no. I think one thing is the energy difference that gives you this gaps, but the heights of the peak I think is experimental artifact. I'm not sure if there is a physical reason. So these gaps actually has a physical meaning. So this is the energy reason. So like we have our quantum dots, so you have like sp orbitals, so the gaps will change, but the heights, I'm not sure why in this experiment the heights are different. It could also be that no, actually not. No.
We have another question. Bhaskaran, yeah.
Hi, this is Bhaskaran from Electrical. I had a question, but before that, this Coulomb blockade peak heights are only a function of basically the many body wave function overlap between n and n+1 states. So they will have different heights. Okay, theoretically. Okay, so I have a question. You are in the 1-1-1 charge regime, right? If I plot the charge stability diagram.
In where?
You have you're having 2 electrons or 3 electrons?
So you can go to different gate voltages and get different electrons.
But right now you are experimenting with 1, 2, 3, right? No.
So in this figure, we have only 2 dots that have electrons in them. The third one is free, like no electrons. But we can put, like later I'll show you charge stability diagrams that are more complicated.
Yeah, because this is a very complicated system. You could have some super exchange effects coming, right? Just because of this.
Super exchange again has a very low energy scale. So it's T square over U. So our T is,
which is J.
Yeah, which is J. But our T is already like 2 orders of magnitude lower than U. So T square over U is.
Okay, fantastic. Thank you so much.
Thanks.
So there is another question by Parth. He's asking how will the extra interaction due to Vij term and mu I term be eliminated?
Oh yeah, that is what we actually do in experiments. So at least at a point, so in our Nagaoka experiment, I'll show, we can tune so that mu cancels out V. All the V components, the addition of all the V's are cancelled out by all the mu's, and that's why you have, like, at this point here, your V and mu are already cancelled out. That's why the energy levels are aligned. So that's what we do. By changing gate voltages, you can locally cancel out mu and V, not globally.
Okay, I think we can continue. There is no more question.
Okay. Okay, so far I have shown you, yes. So the quantum simulation experiment with a 1D lattice, and now from now on I'll go into my experiment. So what I want to do is take this quantum dot system and do a quantum simulation of Nagaoka ferromagnetism. So what do I need? I need a 2D lattice. I'll go for the smallest, easiest one. So I'll go for a 4 dot array in 2x2 geometry.
Sorry, within I probably missed one question. Sumiran, you can ask.
Sorry, could you just again explain that experimental result in the previous slide, bottom right?
Oh, yes. So this was a previous experiment from our group. So what it shows is at lower tunnel coupling, you are in a Coulomb blockade regime, which is a small scale analog of a Mott insulator. Whereas when you increase tunnel coupling, you go to a collective Coulomb blockade regime. So what you see is here, like when you add 1 electron per site here, the gaps are actually changing. But at the collective Coulomb blockade regime, the gaps are roughly equal, and that's what we are like. That's what the experimental result is.
I see. So you're
this is the metal analog of, like, small scale analog of the metal regime. But this is with only three dots. So we don't call it a metal Mott insulator transition. We call it a Coulomb blockade to collective Coulomb blockade.
I see. And what is epsilon 3 in the x-axis?
Oh, epsilon is the filling, or like the energy. So this is what I am calling mu. Sorry, that is bad. Yeah, so this is basically the energy level. So detuning. So you are changing detuning in a, like, so this is a detuning, a linear combination of all 3 detunings. We are changing it in a way that by changing detuning, we are filling like 1 electron per site, one at a time. Like, so 0, 0, 0 to we go to 1, 1, 1 to 2, 2, 2 to 3, 3, 3 to 4, 4, 4. That's all.
And you're tuning some gate voltages to achieve.
Yes, so this is a linear combination of gate voltage, which is like big linear combinations. We call it as.
And then the spacing between the lines at the top being roughly equal is the signature that somehow it is in a metallic type.
Yes.
Sorry, I'm Sumiran. It's hard to hear you.
Yes, for me also.
So I think.
Done actually, but yeah. Sorry. Should I repeat myself?
For me, I mean, I couldn't get the question.
No, so the point is, I was just trying to understand how from these figures I should understand whether it is metal-like or Mott-like, and somehow the fact that at the very top these blue lines are equally spaced implies metal response, right?
Yes, or collective. I'll call it still collective Coulomb blockade response. So there is a paper by Shankar Das Sharma where he kind of explains this. I think it's from 1990s. The Coulomb blockade to collective Coulomb blockade. So the gaps being equal is a collective Coulomb blockade response, which is a small scale analog of metal.
I see.
Okay, I think we have one more question in between. So Riddhish, yes.
Yeah. Hi, Uditendu.
Hi.
Sorry, can you just go back to the previous slide?
Yes.
So it's my question concerns the same diagram that you have from mod to metal.
Yes.
So how is this transition coming out? I mean, I'm just asking.
So you are changing tunnel coupling. So you are increasing tunnel coupling between the quantum dots.
Yeah. So what I'm thinking is, I may be mistaken, but from my memory, I seem to remember that in a 1D, the mod transition is for infinitesimal u. Is this statement wrong or correct?
So I have to double check, but I think you might be no. For 1D, the mod transition is for infinitesimal u when the system size is infinite, right?
Right. So if your
This
transition
is
is coming from true, but if your transition is coming from finite size effect, then it is not a true marker of
yeah,
what
no, that's why we don't claim it a mod to metal transition. We claim it to be a Coulomb blockade to collective Coulomb blockade transition. So there is this there are these questions there. Sure, if you don't go for an infinite size system, if you can call this a clear mod to metal transition.
No, so what I'm trying to understand is the distinction you are making between a finite and an infinite size system is true for any transition, which is whether it's a crossover or a phase transition.
Yes.
So that is different. So here you have a finite system, all things will be a crossover.
Yes.
But what I'm saying is the thing that is driving it, whether it's a crossover or a true phase transition, how does finite size effect relate to a finite u? Because in a true infinite system, an infinitesimal u should drive a 1D system to a mod transition, an insulating transition.
Yes, so I don't think I can answer this question. Sorry.
I see. Okay. Yeah, no problem. I was just curious.
Yeah, sure.
Okay, I think we can continue and then we'll take all the questions at the end now. Is it true? Yeah. Okay, thanks.
Yeah. So, as I was saying, so I want to simulate this Nagaoka Ferromagnetism, which requires a 2D lattice. So for experimentalists, like this is what experimentalists do. We'll go for the easiest one because this is the first time I'll see it. So the system I want is a 4-dot system in a 2x2 geometry. I can't get infinite u, so we'll still do it in a finite u system. And then we need to make these 4 tunnel couplings equal, which is a daunting task. On top of this, what we need is to not have any tunnel coupling between these diagonals. Because in the assumption, in the Nagaoka assumption, there is no next nearest neighbor transition, tunnel coupling. So it's assumed to be 0. So what I need to now show you that I have a system that actually follows this. I can fill, and then I need to fill this system with like 1 less than half filling, so 3 electrons. So I need to show you that I can do that. I can control tunnel coupling, so I can make them equal. And finally, because I'm looking for a ferromagnetic system, I should have some kind of a spin readout. So in the next part of the talk, I'll show how these things are done. So this is an ideal way of how I look at the device. So all these gates, you can see that they have a lead. So they can go fan out of the device and have like voltage wire connecting it. Except for this center circle. So this is another gate which is essential to keep this next nearest neighbor transition to minimum, to 0. But you can't actually have a lead from the same plane. So if I have a lead going through here, the lead would also put voltage. So if I put negative voltage here, there will be more negative voltage here, and I'll never be able to make the tunnel coupling of these two equal to the others. So that's the fabrication challenge. And the way we solved it was by going for a multi-layer gate structure. So I'll show you in step by step how we did. And in this device, I have like 2 sensors here. This is one sensor, that is another sensor. This is my main quantum dot array, dot 1, 2, 3, and 4. And these are electron reservoirs that are present. in ideal scenario. So in the first layer, we made all gates except for the center gate. And this is the design. This is the ACM image. Next, we did a liftoff of a silicon nitride patch, which goes over one of these gates. This is a 50 nanometer thick silicon nitride, which we tested. And we know that if our gate now goes over this silicon nitride, it will not affect the two decks significantly. And then the final gate will have to land at the center. So as you can see that these gates are like 40 nanometer wide. So all these alignments are also quite tricky. But in the final layer, I come with one single gate that travels on top of this gate. So it also negates the effect of this gate separately, goes over this silicon nitride. So this is a tilted SEM image of the device that I made. And then the gate lands at the center of the device. And at the center, it is touching the same surface as the other gates. I'll also show a AFM image of the same device, not showing anything different, but it's a very nice image, at least I like it. So this is the final device where I can make now 4 dots here, 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 and here, and I'll have 2 sensors to measure them. Next, what I want to show you that I can actually fill this system again with any like deterministic number of electrons. So this is another charge stability diagram. Now I'm changing the P4 and P2. So basically gate voltages, this one and that one. I can also change gate voltages like other gate voltages. But in this picture, I'm showing this. And you see that there are 4 different slopes. The lines are 4 different slopes. So if you take one of them, let's say this one, and you do slope analysis with all other gates, you know that this is coming from dot 1. Similarly, you take lines from the other 3, you do the slope analysis, you know that these are coming from dot 2, 3, and 4. And we also know that going more negative in this regime doesn't give us any more lines. So now I can start my counting. So I have no electron in this side. I add 1 electron each in different dots. And thus I can go in this figure, I can go to 1 electron per side. I can even go higher in gate voltage space. And here I can show that I can go to like 4142 and a lot more. Like I can change gate voltages and I can get any number of electrons that you want me to get in this Coulomb boxes. So this is my target 2. So I have deterministic filling of electrons. Next, what I need to do is have tunnel couplings that are quite equal to each other. To do that, we change mainly the gate voltages here, here, there, and there, like the tunnel coupling gate, as well as the center gate voltages. And in this figure, what I'm showing is I was successful in making all 4 tunnel couplings close to say 5 or 5.25, if you will, gigahertz in simultaneously in our system. So this is at one like distance. So like now my quantum dots. So this is slightly rotated. The dots would be rotated in the previous figure. And then I can bring these dots even closer, and I can make them again equal at 10 gigahertz. I can make them equal at different points. I'm just showing two diagrams here. And in practice, I can make them equal between anything between 0 to 12 or something successfully. 12 gigahertz, all 4 quantum dots. So this is my target 3. So I can have a control over tunnel coupling. The last thing I need is a spin readout. So to do the spin readout, I again look at the charge stability diagram. Now this is the 4-dot device, but look that the last 2 dots have the same occupancy for this figure. So let's just ignore that. So here I have 1 electron in first dot, no electron in second dot. If I cross this line, like if I do a pulsing, and this figure looks different from the other figures because I have a pulsing running on top of this. So this is like the effect of pulsing. And that's why you are also seeing this triangle. So this is our readout window. So first, like going from point 1 to point 2, I'm loading 1 electron in dot 2. Then I'm trying to pulse these 2 electrons to the same dot. And my energy levels are aligned in such a way that if these 2 electrons are in a singlet configuration, the energy state it needs to go to is here. So it's below the energy level it has, so it will readily go. Whereas the triplet energy state is somewhere there. So if these 2 electrons are in a triplet configuration, they will not readily go. And if you now measure the charge stability, the charge signal, you'll see that if you are coming from a singlet, you have a lower current than if you are coming from a triplet. Now what happens is, as you were mentioning, the spin orbit and hyperfine, in practice more hyperfine in our system, will drive a spin flip, and it will show a drop to the, like it will indeed go to this 2-0 state by doing a spin flip. But if you measure very fast here, depending on the T1 of this decay, you can measure if if you measure the current here, you can measure if your 2 electrons were in singlet or in triplet configuration. And this is our spin readout. The readout fidelity we measured for our system is 96%, which is actually limited by T1, which is limited by the hyperfine interaction in our system. So now I have shown you that we have successfully got all these requirements to have a proper quantum simulator out of this dot array. And this is actually so far the best control shown in any 2D quantum dot array. But okay, things are changing and probably not for long. And all these results you can see in this paper. So now that I have my quantum simulator, let's see how I can simulate Nagaoka ferromagnetism in this system. Again, I have 4 dots. What I need to do, I need to load 3 electrons, and then I need to let these electrons roam freely in this 4 dot array. If I do a very quick calculation of this 4 dot system, what we'll see is there is for lower T, the ground state is spin 3/2, that is ferromagnetic. Whereas at a higher T, the ground state becomes unpolarized. What happens is the dots comes closer together, and you basically form these orbital kind of structure. They essentially form a single dot. It would be very nice if we could have access to all these regimes like this transition, but unfortunately, I have only experimental access to that window there. But the good thing is, here is in my opinion, the more interesting regime. So the ground state is ferromagnetic. So we should be able to get this. This is these calculations were extended by our collaborators, and the main is still from Nagaoka and Magis. So let's look at something else. So I'm saying that in a 2D array, but what I in principle have is a ring, which is not very far from a 1D system. And there is this theorem by Lieb and Mattis, which says that for a 1D lattice, the state is the lower spin state. So the gap can be small, but the ground state is always the lowest spin state. This is the Lieb-Mattis theorem. So what happens in Nagaoka? So it is nothing but a 1D chain, at least for our case, with a periodic boundary condition. But this answer was also given by Mattis later, and he says that in a 2x2 array, the Lieb-Mattis theorem will not hold, and it would be in the Nagaoka regime because of the hand waving argument that I'll show now. So let's say I have a spin half system here. So I have this hole here in say my site 1, and I want to bring this hole to site 3 here. So I can either rotate clockwise, rotate the hole clockwise and anti-clockwise. And what do I have? If I rotate the holes clockwise and anti-clockwise, I have these 2 states, which if you see are not the same. Whereas if I have a spin 3/2 system and again do the same rotation, you see that the hole has come to the diagonally opposite position, and these 2 systems actually looks the same. And this in practice helps in your tunneling. So this is actually what is encouraging tunneling. So the energy gained by tunneling is more, and that is what is driving your spin 3/2 to be ground state for some tunnel coupling region. So this is Nagaoka, Nagaoka with Lieb-Mattis comparison. Because I also have a control over my quantum dot system, in my system I'll show I'll see if this can be this transition can be possible. So okay, now to the main experiment. So what do? I take my dot system. This is my charge stability diagram that I showed earlier. I go to this point. So this is the voltages that I load. So I have here, I see that I have 1 electron in dot 1, 1 electron in dot 2, dot 3 is empty, dot 4 has 1 electron again. This is the energy level diagram of this. What happens if I slowly come to this point? My dot 1 and 2 energies are still there, 1 electrons are still stuck there. And this electron, which was before in dot 4, is now being shared between dot 3 and 4. So what this tells us is, if you want to share electrons, you need to go to this interdot transition point. We want to share all 3 electrons between all 4 dots. So things will get slightly complicated now. What we need is to align all these interdot lines in the same point. So in a more complicated charge stability diagram, I can see different interdot lines. So Along this line, the energies of dot 2 and 3 are aligned. Along this line, the energies of dot 1 and 4 are aligned. Along this line, the energies of dot 2 and 4, because of how I am plotting, so 2 and 4 doesn't have a tunnel coupling, but the energies can still be aligned. So if I bring them closer and closer, at this point here, I'm actually aligning all three interdot lines. So I'm aligning all four energy levels. And now my electron can move freely through the lattice. And this is where I expect the ground state to be ferromagnetic, to be Nagaoka. I'll plot again the same charge stability diagram, but slightly differently. So you see that now my gate voltage is a linear combination, and the reason will be clear in a minute or so. So here, So I have this point where again my different charge stability, energy levels are aligned. So my all four energy levels are aligned. My electrons are moving freely through the system. Assumption is here my system is at ferromagnetic state, but I can't measure this 3 electron magnetism in my system. For that, I need to do a projective measurement, and that's why I plotted this system in this way. So this is a simulation of the charge stability diagram. Because this has a large range, I can only do experiment in parts of it. So here I show that the experimental picture of this box part here looks like that. So what I do is I do a quick pulsing from this Nagaoka point to the measure point. Here, by doing this pulsing, I'm randomly taking one electron, confining it to dot 4. I'm making dot 3 empty, and I'm measuring whether the other two electrons are in singlet or triplet configuration. What do I expect? So if I have a spin 3-hub system and I do a projective measurement to a 2-spin triplet, the probability of getting triplet is 1. Whereas if I have a spin half system and I do a projective measurement of getting a triplet for a spin triplet in 2 spins, the probability of getting triplet is 0.5. So if I do this experiment over and over again, and I measure the kind of triplet levels I'm getting, I can tell whether I'm coming from a spin half system or a spin 3-hub system. So that's what I do in the experiment. So remember these points. So this is the Nagaoka point, this is the measurement point, and this is the line that we are using for measurement. And this is again a simulation of this along this line. So at the measurement point, the ground state is a singlet in dot 1 or 1, 2, the way if you are slightly this side of the detuning, and then there is one electron in dot 4. At the Nagaoka point, we see that there is a crossing. Now, in this picture, I have not shown that there is an avoided crossing. This looks like a proper crossing, but because I haven't incorporated spin orbit and hyperfine in the calculation. Once I put them, these will be not a crossing, but avoided crossings with those energies. But at Nagaoka point, there is a crossing and the ground state is spin 3-hub. So what I do is I initialize my system here with singlet and 1 electron. I go to different detunings. I go there slow and fast, but I come back fast and I measure what kind of triplet proportion I'm getting. So this is the result of the kind of the first experiments that we did. So at lower detuning proportions, before we have reached this crossing, we see that the triplet fraction is very low. It's not 0 because of some kind of initialization error that we have in our system. Also, when you are pulsing, there is a slight probability that you might populate one of these states. Now, what we expect is when we are going here, the triplet proportion will rise. In practice, in one of our first experiments, we saw that it's not a single peak, but a 2-peak single dip kind of a structure. And if you think about it, this is happening because you are crossing this anti-crossing, this avoided crossing too fast. So these 2 peaks are coming when you are actually going to these detunings where you have mixing some kind of. But when you are actually going to the Nagaoka point, you are going to spin half state. Now, remember, when I'm going from singlet plus 1 electron to this point, my electrons are not mixing. What comes back is singlet plus 1 electron. So it should be singlet. Whereas if I'm going here, what comes back is a 3-spin spin half, which has a measurement probability of 0.5. So you would still expect to see a higher triplet fraction, but not as high as you would expect to see coming from this. So the obvious next step would be to pulse slower and slower. And that's what we did. If we pulse slow through this anti-crossing, so if we indeed end up here, we see that instead of this 2-peak 1-dip kind of structure, what we see is a single peak. So comparison, so if we pulse diabatically, we see this structure. If we pulse adiabatically, going in, we see this structure. Going out, we always pulse fast. Okay, so now I claim that this structure, like this difference, so this is a signature of Nagaoka Ferromagnetism in our system. I claim that this difference is coming from the spin orbit and hyperfine interaction. Let me show you if the numbers actually make sense. So in the next simulation, what I'll do is I will now incorporate both spin orbit and hyperfine in the simulation also. And also I'll not just do the two like extreme speeds, I'll do intermediate speed. So we now traverse this gap with intermediate speeds. And if I now measure the triplet fraction at like around detuning proportion 1, you see that depending on the speed you are pulsing, like the pulsing time, your triplet fraction is changing. If I now incorporate my spin orbit and hyperfine, my energy diagrams look like this. Part of the energy diagram looks like this. And we used a home-built density matrix solver. And for that, so now I have both hyperfine and spin orbit. The hyperfine is comes as a kind of an average Overhauser field, whereas spin orbit is direction dependent and also depends on the gap, like the distance between two dots. Lithographically, the distance between the nearest neighbor dots should be 150 nanometer. So we did the fitting for 3 different spin orbit regimes, like between 100 and 200 nanometer. We are quite confident that the distance between two dots would be like between 100 and 200 nanometer. And for this kind of spin orbit, taking into the orientation and spin orbit into account, the hyperfine Overhauser field value that we get is between 70 to 76 nano eV. This is matched very well with the previously known Overhauser fields in gallium arsenide wafers similarly produced. So they come between 70 to 80, 85 nano. That's the number we get. So this is very encouraging that we indeed expect to see these kind of effects from the spin orbit and hyperfine interaction. Now, one might argue that I'm playing a lot of jugglery with speed, but my ground state is ferromagnetic. Why don't I just go to this point, wait long enough, and show that my ground state is ferromagnetic? But there is a small problem there. If you see in this energy diagram, you would see that the gap between the ground state and the Nagaoka ground state and the spin hub state is 4 micro eV. If you remember when I was first introducing my quantum dot system and comparing it to how good Hubbard model simulator it is, the temperature I quoted was around 6 micro eV. So the temperature is actually higher than this. So we can't wait long enough. What do we expect? We can wait long enough, but we won't get the ground state. What do we expect if we wait long enough? Doesn't matter if we pulse fast or slow. We'll go to an intermediate triplet fraction, which is basically a mixed state. And that's what we get. So it doesn't matter if we ramp fast, like with 5 nanoseconds, or we ramp slow with 1000 nanoseconds. If you wait long enough, like 10, 12 microseconds, the triplet fraction would be the same. Okay. The next thing I'll do, just a minute. The next thing I'll do is try to see if our system also holds the Lib-matrix criteria. So I already claimed that I have very good control over tunnel coupling. So let's do some things. So this is my, again, Nagaoka criteria. So the tunnel couplings are roughly equal. We see that this signature of going diabetic and adiabatic. I'll start opening this tunnel coupling. So I'll start opening this ring to a chain. This is, I'm reducing this tunnel coupling. It goes from 16 to 8, 15 to 8. And you see that the signature starts to go away. I'll go to 0 tunnel couplings. You see that there is no difference now between going diabetic and adiabatic. And we tried with even more extreme pulse speeds, and there is still no difference between going diabetic and adiabatic, which means that there is no actually crossing between levels. And if you do the simulation of energy levels here, you would see that the expected energy level ground state, as predicted by Lib-matrix, is the spin hub. So you go to the spin hub, you come back, so you expect to see about 50% triplet, and that's roughly what you are seeing. Okay, so that's well and good that if we go from a ring to a 1D chain, the Nagaoka signature goes for a Lib-matrix signature. The next thing is really interesting. So this is the effect of a perpendicular magnetic field to this system. So now, when we think about ferromagnetism, any magnetic field you apply on this system.
So let's try to finish it in 5 minutes, maybe.
I think I have
take one more question. Yeah.
I have 2 more slides.
Okay. Thanks.
Yeah. So the first thing is, if you put a perpendicular magnetic field in any magnetic field, a ferromagnetic state basically is it should help ferromagnetism, but not here. Because what you get here is a hole is going around this field, so it will get an Aharonov-Bohm phase. So depending on the magnetic field you put, you would actually expect to destroy ferromagnetism, and then at a higher field, when you have a 2 pi phase difference, to bring it back. But life is not that fair. We are working with electrons. It's not only the Aharonov-Bohm kind of phase that you will get if you put a magnetic field. You will also get Zeeman effect, and then you get a whole big mess of energy levels as soon as you go out of your zero field. So we still try to do the experiment, and what we see here is now going slow is not an option, because you see all these, even before reaching Nagaoka, all these levels are so close. If you go slow, you will mix the state. If you go fast, you'll still mix the state, but you still see some kind of like going from 0 to 16 millitesla. This like 2 peak 1 dip kind of structure kind of goes away. Now I understand that this data is significantly not clear as respect to all other data in our experiment, but this is the best we could do with respect to magnetic field in our system. The last thing I want to show is this detuning of local energy. So this is not something that was studied before on Nagaoka like theoretical models. So this is the typical Nagaoka setup. What happens if I now detune one energy level like this or like that? So what we see, surprisingly, is the Nagaoka condition still survives up to some some detuning, and this thing is actually reproduced in simulation also. So this is a qualitative analysis. So like for plus detuning and minus, you see that either this gap becomes narrower or broader, and also in experiment you would see that the same thing happens. If I actually do this quantitatively, if I measure this detuning gap between these two and like say these two, for say 1 dot for even higher detuning, you would still see that the gaps are pretty close to what you expect from simulation. So this is very good. So with that, I'd like to conclude our experiment. So what I have shown here is this is the first experimental signature observation of Nagaoka ferromagnetism in our system, in any system in experiments. We showed that our system also obeys the lattice theorem. Perpendicular magnetic field can destroy ferromagnetism, kind of, and also this Nagaoka ferromagnetism is robust to local offset of one energy level up to some extent. This is already a surprising result, which is verified by simulation. The final thing is we also, so all these simulations before we were assuming that our system is a Hubbard model like analog. In this paper here, our collaborators with us actually did an ab initio calculation. So we did not truncate our system to like two electron per side. We allowed we took some 4 Gaussian potential well. We allowed up to 16 energy levels, and then did the entire calculation, which was a significantly like hard simulation with respect to this one. But still, all these results match with this ab initio calculation as well. So if you want to learn more about these ab initio calculations, you should read this paper. So finally, I would like to say that this is like one experiment, and we can do several other experiments like this. So first, let's say the other experiment that we were planning before I finished my PhD was to see this resonance valence current, the RVV kind of state. So as Anderson predicted, if you have this kind of a structure, you can't have singlets both in this and in this direction. So you would have an oscillation between vertical and horizontal singlets. And because we can do correlation measurements, if we do repetitive measurements of like say singlet proportions here, we would be able to, or we might be able to show this. So this is one thing. There was one question about scaling. So I have a plan to scale to say at least to a ladder structure. So note that this is not yet a device I've made. I just copy pasted the same device next to each other, but it shows that there is no, at least in principle, there is no problem in going to say a 2x4 or a 2x8 kind of structure. There are several nice experiments one can do. One thing that you can think of is like you can study pairing of holes here. Let's say I introduce one hole here and one hole here, and I put electrons in all the other sides. We can see if we allow these electrons to move around, if in some condition pairing of hole is encouraged or like kind of comes out more than other conditions. This is something we can study with this kind of system. Also, there are like in 1D system in our group, we are now trying to simulate 1D Heisenberg chains like Heisenberg antiferromagnets and all. So with that, I'd like to finish and thank my amazing group. So this is Leven here, the boss, and JP, who worked with me in the entire project. Like we worked together in this entire project, and also all our awesome theory collaborators. And thank you for attending this talk. Now I'm ready to take questions.
Thank you very much for this nice talk, Uditendra. So we have a few questions. So let's Bhaskaran ask the first question.
Yeah, I have a question. Can you go back to this diabatic versus adiabatic? So first of all, you talked about the Overhauser field, but there's also the nuclear relaxation time constant, which is very important, which will actually govern the fact that, how much Overhauser field builds up really is a,
so this,
on the, because that runs in seconds, right? Or maybe milliseconds,
The nuclear field, like the nuclear relaxation is not that fast. And all our experiments are done in like microsecond region. So I don't think the relaxation.
But in adiabatic case, then you should have.
It's still in milliseconds.
Okay. So where is this slide you showed about the Overhauser field that happens? I just wanted So basically, your thing is that you have a triplet fraction that is modulated due to the hyperfine interaction flips between singlet and triplet, right?
No. So you are crossing this anti-crossing. So depending on how fast you are crossing, those anti-crossing is coming from Overhauser and spin orbit, more from Overhauser. And depending on how fast you are crossing this intercrossing, you will either go here, which is the ground state ferromagnet, or you will go here. And this like simulation actually matches the already known Overhauser field value.
This well-known energy landscape of the double quantum dot.
Yes.
Okay, thank you.
Thanks.
There is another question by Sai. He is asking, what is the definition of diabetic versus adiabatic?
So for like the definition would be adiabatic is like in our experiment, the definition is when in diabetic we go fast enough that we completely cross this and we don't have like a mixture of crossing, like we only go here, and for diabetic we only go there. That's how we think of adiabatic. Like when I call something diabetic and adiabatic, I'm saying like if I change, like if I make my pulsing even more slower, I'll not see any more change. And if I'm going here with adiabatic pulses, diabetic pulses, if I make my pulses even faster, I'll not see any more change.
No, this is fine, Uditendra. I was just wondering where the energy level diagram was with respect to which you were making the kind of,
No, this is
argument.
This is this diagram.
Yeah, you already brought it up in the previous question. Thank you.
Yeah.
So we have one question from YouTube by Kanti. Is asking, when you go to larger number of dots, do you multiplex the gates or just have very large number of leads in the whole device?
This is a very good question. You definitely have to multiplex number of gates. You can have connected gates. That is the dream. Like if you have a system like a TUD that is very nice and like there is no local inhomogeneity between like spaces. What you can do is you can have small gates, but they can be connected to each other. So then you don't need so many leads, because for this I need like 19 gates to make 4 dots. I can't go to like 10,000 dots with them. Like I can't make 19,000 gates and have 19,000 leads to it. So we can make multiple gates. I don't think there is a big problem there, as long as you can connect them somehow and not have same number of leads. So we need leads ideally like within 1,000 leads. That's how like the classical processors also work.
Okay, thank you. So I have a small question. So my question is that when you talked about this outlook, you talked about a ladder system as well as a Heisenberg and all this kind of system.
Yeah.
Is it true to assume that you don't have a control over the hopping? So other way of saying that the interaction between the dot is local. Is it the best you could do? Or?
So you want inter-site interaction, not more than next nearest neighbor?
No. How is it for the system? I'm asking. So.
Oh no, if you so you have to change the design. If you want, like in a small scale system, I can make next nearest neighbor interaction. Like even with this system, if I take off the voltage on the middle gate, I can get like diagonal interaction. But for us, like large scale device, next near like long distance interactions would be hard. So
Okay. So any other questions from the audience? Doesn't seem so. So let me then ask one more stupid question. So you also showed us that what you want to do in the outlook, but let's say, fine, all these things is kind of very interesting to see in a quantum dot setup. But what would be the next physics that you would like to understand from this setup? Let's say you have this 4 quantum dot setup. From the physics point of view, what would be? It's not the technical part I'm asking. I'm saying that.
So if I can go to, so these proposals we always get from talking to theorists. So I don't have clear idea of exactly what is the scope of things that can be done. But I know a few things that we can do, like what I was talking about, the resonance valence band system. So that's something, it is, I think it's not a low hanging fruit, but like a medium hanging fruit that we can try. If we can go to a ladder structure, a large enough ladder, and study pairing of holes, that would be something of like a great interest for me. And a Heisenberg chain that I think is already coming in like the next year or so. So people are already working on it on the devices that we made.
So and also you can make all this frequency dependent measurement as well, or is
yes.
it difficult?
So no, it's not difficult. So you have to just connect. So like people do that in quantum computation setup, right? So all I have shown here is same as what one would do in a quantum computation setup. So if you go for silicon, so you need some kind of a splitting between spin up and spin down. So you need some kind of like a magnetic field or something. But other than that, everything is actually done. So and then people do exchange oscillations. So even for this experiment, what would be really nice if we can show this exchange oscillation between like these two states. Like if you can quickly drive an oscillation between these. And this is possible, although quite hard because of for this experiment, for the energy scales involved. But if we can like attach a few microwave lines and a microwave source, we can also do frequency dependent measurements. Sure. Because people have already done that.
But in that case, sorry, this is Shuddho here.
Yeah.
Yeah, but then in that case, you will run into the trouble of selecting which dot to address, right? I mean,
so this is a cumulative effect. So here you would not, but in like if you want to address one dot, then you have to have something like a difference between Siemens splitting between dots. Like how people do it.
But in this case, you are saying
this is a collective effect. So this is a spin 3/2 3 spin effect. This is a spin half spin effect. So here you don't have to address that.
Okay. So you could just have a global cavity and then an antenna just supplying the microwaves.
Yes, ideally.
Okay, Uditendra, I think I have one last small stupid one. So this ladder system seems very interesting. So if let's say, as you said, so you can control the hopping, and let's say you also mentioned that the magnetic field is possible.
Yeah.
So in that type of system, is it also possible to control the magnetic field locally? Means like individual level? Like I can think of it as a flux within the 4, and it's possible. You said.
So what we did is we have a big magnet inside the fridge, and we place this system perpendicular to the magnet. But what people do in quantum computation actually with silicon, so they make these local like micromagnets. So by designing micromagnets, you can actually have this magnetic field gradient along different lines. You can have a gradient along X, you can have a gradient along Y, and like but the micromagnet design would be slightly tricky. But anyway, and this would be like something like a nickel micromagnet on top of this entire structure. So you put something like a dielectric layer on top of everything. You'll put a micromagnet with specifically designed for the gradient you want, and then you can have local gradient in magnetic field with micromagnets, but not with this kind of like with adding one more layer of micromagnet.
Yeah, but to the order of some 10 to 50 millitesla, not more. I mean,
yes,
that's the kind of.
That's quite a large also.
Yeah, okay. I'm thinking of the global field, probably not.
Right. Thank you. Okay, let me thank Uditendra Egun for this very nice and interesting talk on things that we don't hear that much these days. I also thank all the participants for joining for the Zoom meeting. So we'll have our next seminar in the next week as well. So again, Uditendra, thank you very much for this talk.
Yeah, thank you all for organizing and also attending. Okay.
Thank you.
Yeah, bye.